It is my great pleasure to introduce Professor Gordon Blower with the title Linear Systems and Differential Equations in Random Matrix Theory. Welcome, and we're sure we're going to have a great talk. Thank you.
Thank you very much for the introduction. So I'd like to wish the audience a good afternoon or a good evening, depending on where they are. This comes partly from joint work with Ian Doust, University of New South Wales, and also mentions some things later on associated with work in conjunction with Yang Chen, University of Macau. General plan of this talk, I'll begin by introducing familiar definitions from the theory of linear systems in continuous time and Hankel operators. Then I'll return to a topic of Howland operators and consider how they're related to linear systems, and then introduce a tau function which is associated with linear system and also with the sinh-Gordon equation. And then I'll proceed to discuss how this is connected to a certain Hankel determinant and solutions of a very particular transcendental differential equation, a special case of Painleve III. Now, much of this work was motivated by or is associated with Tracy Weedham's theory of random matrix models, and I'll describe the connection further on the talk. And then, having established the connection with random matrix theory, we can use some of the results from that. And I'll mention a free logarithmic Sobolev inequality, which gives some more information about some of the solutions of the systems that we're discussing. So, begin with what are, I imagine, familiar ideas. I'm going to be talking about a linear system. I tend to write minus A, B, C, and think of A as being positive, for instance. The H here is a separable complex Hilbert space of infinite dimension. H naught is going to be a finite dimensional complex Hilbert space, usually either the complex numbers or the square of the complex numbers. And H naught is taken as the input and output space of this linear system. On the state space, we're going to take a strongly continuous semi-group, e to the minus TA, and just for simplicity, we can take the operator norm of e to the minus T naught of A to be strictly less than 1 for some positive T naught, and that's going to make sure that various integrals converge. So we have minus A going from the domain of A to state space H. The input operator goes from the input space H naught to the state space, and then the output operator C takes us back from the state space to H naught, and the output space is coincidentally the same as the input space. Now, given this information, we can construct what I'm just going to call a scattering function, in which you apply B first, then the semi-group, e to the minus TA, and then C, and this is phi of t, and this object is going to be used basically to construct Hankel operators. In the general theory of linear systems, there are controllability and observability operators. So the observability operator goes from L2 with values in H naught to H. The definition of this involves some adjoints. So we take C adjoint, and then we take e to the minus SA adjoint. Again, this is going to give a strongly continuous semi-group. And under the assumptions above, I can form this, this integral without difficulty. The controllability operator psi naught goes in the same direction. That's, say, L2 with values in H naught to the state space H. We don't need any adjoints this time. We just apply B first and then e to the minus SA and then integrate. A relatively novel idea is what I'm going to call the R operators. These have appeared implicitly in many papers over the years. I've been sort of studying them fairly systematically, and these operate on the state space itself. The idea is the operator BC goes from the state space to itself, but is going to be an operator of finite rank because it factors through the finite dimensional space H0. So if we apply an e to the minus TA on the left and on the right and integrate, there's a good chance that this operator RU is going to be trace class. So that's one reason why one wants to study this object, and it turns out to have some significant properties. More familiar object is the Hankel operator, gamma phi. This is going to be defined on the L2 functions with values in H0, and we get this by the familiar formula in which we take 5x plus y and integrate that against f of y dy, and the integral runs from 0 to infinity. So the linear system is going to be set up so that we've got minus a, b, c, and we can let time evolve. And as time evolves, the operator A is going to stay the same, but one can think of B as evolving to minus UA times B, and C is evolving to CE to the minus UA. And evidently, the effect of this on the R operator is to go from R0 to R subscript U, which is what you get by multiplying on both sides by e to the minus UA. So this is kind of symmetrical, and we also have an effect on the scattering function in which we basically replace x by x plus 2u. Now you get 2u because you've got a u on the left and the u on the right, basically, and this basically shifts the scattering function. It's evident from the formula on this frame, also it's evident from the integral definition, that the R is going to give a solution of Lyapunov's equation in which we differentiate with respect to the parameter u, and we get minus a times ru minus ru times a. Now, differential equations of this form, or things like it, appear frequently in the fundamental work of Peller, Magretsky, and Trail on the spectral theory of Hankel operators. So this Lyapunov equation appears in a slightly different form elsewhere in the literature. Sometimes it appears with adjoints in the cases in the literature, but in this formulation here, I don't have any adjoints. The actions on the left and right are symmetrical. Now, the reason why R and A are easy to work with is that we can generate a sort of ring of operators on the state space, which is closed under differentiation with respect to the parameter u. One of the unattractive features of Hankel operators is that the product of two Hankel operators is not Hankel. So what we're going to do is work with operators that do have a multiplicative property and have got better properties with respect to differentiation. So that's one of the reasons why I prefer to work with RU rather than Hankel. Also on the linear system, there is a rather obvious operation of replacing C by minus C. And just to give it a name, I'm going to call this the Darboux map because it is associated with the operation of Darboux addition in the sense of the spectral theory of Schroedinger operators. Now, next topic is to talk about Howland operators. In the early 1990s, Howland considered operators that are either Hankel or closely related to Hankel. They're integral operators in L2, and they have a special form the numerator is b of x times c of y, and then you divide through by x plus y. Now, if for the moment we take b equals c equals 1, we get the famous operator 1 over x plus y, and this is sometimes called Carlemann's operator. Now, in Power's book, Hankel Operators in Hilbert Space, there are various exercises in which the reader is invited to transform the Carlemann operator into numerous matrices and operators that are all sort of unitarily equivalent to the Carlemann operator, but don't look anything remotely like it. So it is possible to carry out various transformations on Howland operators that sometimes preserve unitary equivalence, but you can make transformations into things that look very different. And we're going to be using some of these transformations in the course of calculations. Now, Howland made an observation that Hankel matrices are in some respects analogous to one-dimensional Schroedinger operators in which the role of the Laplacian is played by Carlemann's operator. So the idea was that some of the results from one-dimensional Schroedinger operators have got counterparts for Howland operators of this form. If we choose the b and c to be functions with scaling properties, and I'm just thinking of powers like b of x is x to the alpha over 2, then this operator has got some sort of scaling when you multiply x and y by t. Now, this has been exploited in various papers because you can construct Howland operators that commute with families of differential operators. And there are ways in which one can sort of diagonalize Howland operators with respect to certain families of special functions. So on account of this, Howland operators are quite a natural way of starting to construct solutions of Painleve equations. And I'll give examples of this later on in this talk. Howland didn't really spell out the connection between linear systems and Howland operators, so I'm just going to do this here. The construction is relatively straightforward. I'll begin just by talking about the operators. We're going to be taking the state space to be L2 on the positive semi-axis, and the main operator is basically A, which is just multiplication by X. To get the B operation, you just take a scalar and multiply by a fixed function B of X. To get to the output operator, you just integrate your function against a fixed function C of X. And when you form the scattering function, you find that all you're doing is basically calculating the Laplace transform of the product C of X times B of X. So that's a fairly natural thing to do. And the corresponding Howland operator is what we were discussing a moment ago, namely B of X times C of Y over X plus Y. Now, under the conditions stated at the top, namely that C of X over root X and B of X over root X are L2, then this operator R0 is Hilbert-Schmid, and one can show that the corresponding Hankel gamma phi is also Hilbert-Schmid. Now I want to sort of make more stringent assumptions. Let's just suppose that the controllability and observability operators are Hilbert-Schmid. Then the products one can form from these are going to be trace class. And when an operator is trace class, it has a well-defined Fredholm determinant. So in the circumstance here, we're going to have R0 and gamma phi trace class, and we're going to define the tau function of minus ABC to be the Fredholm determinant of R subscript X, and also the Hankel operator gamma with the scattering function phi translated through X. So X is basically a translation parameter, associated with shifting of the linear system. Now, the terminology tau function is used for many different objects that one hopes are related. Classical examples of tau functions include Jacobi's elliptic theta function. And it is possible to construct linear systems for which the Jacobi elliptic theta functions are the corresponding tau functions, using various classical formulas for this. Now, that consideration leads us to consider what kind of differential equations these tau functions might satisfy. If we take hyperelliptic algebraic curve, on such a curve, there's a special vector field, and there's also theta function defined on the Jacobian of the curve. And you can apply this vector field to things like the logarithm of the theta function. Now, there's a general result that if you take the second logarithmic derivative of theta, it gives you something rational on the curve. The prototypical example is take something like Jacobi's elliptic function theta1, and if you take the second derivative of that, second logarithmic derivative, you get something like the Weierstrass function. And there's another related construction. If you take the quotient of two theta functions, take the logarithm and then differentiate that, you also get a rational function on the curve. So these are two ways of producing rational functions on this algebraic curve. Now, in Mumford's treatise on theta functions, he constructs solutions to various partial differential equations from these theta functions. He takes constructions of nonlinear Schroedinger, I should say really nonlinear cubic Schroedinger, Korteg de Vries, modified Korteg de Vries, and sinh-Gordon. And for sinh-Gordon, you have two active parameters, time parameters t1 and t-1. You take a function s and you take the second derivative of s with respect to t1 and t-1, and twice that gives you the hyperbolic sine function of 2s. So that's what sinh-Gordon is about, and I'm going to show how this can be constructed via linear systems. There are, of course, many possible differential equations one can consider in this context, but there is a special class of them. Given a theta function defined in the first instance on a typical abelian variety, one can consider the differential equations that satisfies. And if it satisfies the differential equations of the KP hierarchy, it turns out that the theta function actually must arise as a theta function from some algebraic curve. So this result is a way of identifying the particular class of theta functions that are associated with algebraic curves, as opposed to those that are just constructed from general abelian varieties. Now, this result suggests strongly that the KP hierarchy is the natural kind of system of partial differential equations to look at in this kind of context. There are many things one could consider, but this result suggests to me that the KP hierarchy is the sort of first one should be considering. And one member of that is basically sinh-Gordon. So bearing that in mind, it seemed to me fairly natural to look for solutions of this particular differential equation in this context. And the linear system that produces them is exhibited here. So we're going to take the state space to be L2 of the half-line, we're going to take a bounded and continuous function h. It doesn't greatly matter what one chooses. I'll make a specific choice later on to produce some very specific kinds of solutions. But we have a similar setup to what we had in the construction for Howland operators. The operator A is multiplication by x. B is given by multiplying your scalar beta by h times an exponential. Now, this exponential factor is particularly chosen. I take t1 times x, and then I take t minus 1 and divide through by x. And if you want this thing to converge, you better start taking t1 and t minus 1 to be negative, because that certainly helps. And you make a similar choice of function for c, and the output operator is given by integrating f against h and this exponential factor. So these are parameters t1 and t minus 1 are going to be negative to help with convergence, and I don't write them explicitly in the operators just to keep things relatively simple notationally. Now, for such a linear system, the scattering function is given by the usual formula, c against e to the minus ta, and what we get is integral, which, as before, is a Laplace transform with Laplace transform parameter t, and we're integrating up x, and then we've got these two other time parameters, t1x, and then we've got t minus 1 divided by x. And then the R operator is given by the formulas before. You take BC, then you multiply against the semi-groups, you integrate, and this has the form of kernel that you'd hope for a Howland operator. The first bit's obvious, h of x, h of y divided by x plus y, and then the exponential factors have been so chosen that we end up with an expression x plus y, another one x plus y, and then 1 over x plus 1 over y. So these are allowed within the construction of Howland operators. If you choose your h to be real valued, you get something that's going to be self-adjoint, and we can make sure this thing converges by taking u to be positive and t1 and t minus 1 to be negative. Now, if we take our u to be big enough, then we can obviously make this operator ru fairly small. So it turns out that we can make I plus or minus ru invertible. And now I'm going to sort of introduce this sinh-Gordon equation. There's a slight scaling needed in the u and t1, basically multiplying through by 2, but we can write it as d2s by du dt minus 1 is to be sinh of 2s. And this s function has 3 parameters, t1, t minus 1, and u, and the u is a shift parameter for the linear system. Previously, I mentioned that we want to be considering the logarithm of the quotient of tau functions. So what we do is we take a tau function, which is the determinant of I plus ru, and then we take the determinant of I minus ru. And this choice basically puts us in the same kind of context as the classical way of constructing rational functions on curves. So we're basically going to be taking a logarithmic difference for slightly different linear systems. The sinh-Gordon equation is associated with a pair of coupled ordinary differential equations, which I've written down here in terms of the variables u and dt minus 1. Now, the one at the top also involves an extra sort of spectral parameter zeta, and it's got this partial derivative of s with respect to u. So this ds by du is going to be something you can think of as being a counterpart of a rational function. And then we have another differential equation in the parameter t minus 1, and this involves the hyperbolic cosh of 2s and sinh of 2s. Now, the observation is that this pair of coupled ordinary differential equations is basically a lax pair, and the pair of coupled ordinary differential equations is consistent if you have a solution of the sinh-Gordon equation. And Tracy and Wiedem showed that the linear system that I gave in the previous frame basically gives you solution of the sinh-Gordon equation. And what I'm going to do presently is basically show how you end up with a solution of this pair of coupled ordinary differential equations, which shows that you do actually get a solution of sinh-Gordon. The setup begins with minus ABC, and we want to have the linear system giving I plus RU, and also I want to make a slight variation and consider minus AB minus C, which is going to give me I minus RU. These were the two operators that I needed to form the expression S. So we put these together in a slightly unexpected kind of way. I want to build a system of block operators. It's not surprising we take minus A and minus A running down the diagonal to give me A hat. It's also not surprising that we take C and C running down the diagonal in the last entry to give C hat. The surprising one perhaps is the middle one where I put the B on the cross diagonal to give me B hat. Then we construct the corresponding scattering function, which is a matrix valued function by the usual prescription. So it's C hat, A hat, and B hat. And we end up with the previous scattering functions on the cross diagonal. And likewise, when I form the R hat expression, it is given by taking the previous R, but again, this is on the cross diagonal. In the circumstance in which I plus or minus Rx both invertible, we can proceed to form the inverse of I plus R hat. And by doing some elementary row operations, you can find out what this object is. It's basically going to involve I minus R squared to the power minus 1. And then we've got basically multiples of that against I on the leading diagonal and multiples against minus R on the cross diagonal. Another auxiliary operator we can construct, I'm going to call T hat. Now, this is not symmetrical in X and Y. In the X variable, I take e to the minus xa hat and multiply this against the inverse of I plus R hat. Then in the right half of the formula, I take the Y variable, and that just involves e to the minus y A hat against B hat. And when I work this out using the previous computations, I get a 2x2 matrix, which is symmetrical, with W on the diagonal and V on the cross diagonal. The W on the diagonal begins with CE to the minus XA, and then it's got an expression involving RX, and then the Y term, which is slightly different for the V term, which doesn't have such an RX in the middle, and starts with a minus. So these are slightly different operators that appear in the 2x2 formula for T. Now, the purpose of doing this computation is to get a solution of the Gelfand-Levitan equation, in this case, Gelfand-Levitan equation with 2x2 matrix entries. So this involves phi hat of x plus y, t hat of x, y, and then an integral running from x to infinity of t hat of x, z, and that multiplies phi hat of y plus z, and we integrate in z. And the solution of this is given by a formula that I had on the previous frame, and this motivates the definition. Once you see the formula here and do some simple calculations, you'll see that it does actually satisfy the equation as above. So we then have to calculate some derivatives in terms of the operators, and this is where things start to get a bit more involved. There are many ways of expressing this calculation, some of which originate with the work of Purper in 1980s and 1990s. Actually, McKean suggested to me that I look at this to see how to proceed. The version that I have here involves this R operator rather than the Hankels themselves, but is in some sense a reformulation of the ideas that Purper had. But anyway, we take this I plus Rx inverse, and we use this to form a bracket operation in which we pre-multiply by c e to the minus xa times f, and then we post-multiply by fe to the minus xa times b. Now, this expression doesn't involve any y's, it's x's throughout. Now, when you differentiate this formula, you're basically differentiating all the terms that involve x. Now, obviously, you're going to get a term involving the derivative of p with respect to x when you take the bracket of p, but you've also got to watch out for the derivative terms that arise from e to the minus xa at the start and the end, and you've also got a derivative of f. Now, the reason Lyapunov's equation is important is that it tells you what the derivative of f is, because you know what the derivative of r is from Lyapunov's equation. So based on that, you can differentiate this bracket and you get the formula that's written here. So the first component is the derivative of the left side of the bracket, then you get the partial derivative of p with respect to x, and then you've got the derivative of the right half of the bracket. So you can calculate v in terms of the bracket and w in terms of the bracket and work out some derivatives. And after a moderate amount of computation, one can show that the derivative of vxx, that's the derivative along the diagonal, can be expressed as minus 2 times the bracket of a, and then we've got minus 2 times v of xx squared. Now, this is related to the derivative formula that one gets from differentiating wxx, and that one produces minus 4 vxx all squared. So there's a relationship between the derivatives down the diagonal of v and w. Now, based on this, we can proceed to the solution of the coupled ordinary differential equations. The idea is you take your solution T of the Gelfand-Levitan equation and you integrate this against a vector which is going to depend on constants alpha and beta, and we've got e to the minus I z times zeta and e to the plus I z times zeta. So that's inside the integral, but the main term is basically the term in front of it, which is alpha e to the I zeta u and beta e to the minus e to the plus I zeta u. this satisfies the differential equation d2 psi by du squared, and the matrix differential equation has got minus zeta squared on the diagonal and ds by du all squared on the diagonal, and the cross diagonal terms are the second derivatives of s with respect to u squared. Also, when you take u large, the main term is basically given by the first summand, and the integrated term is relatively small. And you can compare that with what arises from the original differential equation, which I've reproduced here. That said that d psi by du was a term involving ds by du, and on the diagonal and a minus I zeta and a plus I zeta. When you differentiate that again, you end up with a second order differential expression, which is going to involve minus zeta squared on the diagonal and also ds by du all squared. And then obviously there's going to be a second derivative term of s off the diagonal. And you can identify these terms with the corresponding derivatives of t hat using the formulas that I indicated on the previous frame. So that's how the sinh-Gordon equation gets involved. And I want to move on to discuss other differential equations that arise in this context. We're going to consider a Hankel determinant, and it's going to be for what's called the deformed Laguerre weight. The Laguerre weight involves power x to the alpha. So we're going to introduce this by taking the linear system from frame 9, and the special choice of h of x is going to be x to the alpha over 2. So when you take h squared, then you get x to the alpha. Now the standard Laguerre weight is x to the alpha e to the minus x. Chen and Itz considered a perturbed version of the Laguerre weight in which they put in the exponent minus s over x. Now this is a rather drastic thing to do, because this perturbed Laguerre weight is going to have a very strong zero at x tending to 0 from the right. So this Laguerre weight is going to go to 0 very quickly. Now it's known as a singularly perturbed weight because this weight goes to 0 so fast that the classical Shegu conditions of orthogonal polynomial theory do not hold for such weights. So one of the reasons why Chen and Itz were interested in this was to consider Hankel determinants in contexts that are violating the conditions of the strong Shegu theorem. Now they carried out an analysis of the Hankel determinants, and I'll just take t equals 1, t1 is 0, and t minus 1 is minus s. So we get something of the same kind of character as we had before, except that now I'm treating the main variable as being this t1 is minus s, and the other ones are fixed. So we form the product of the Laguerre, modified Laguerre weight against x to the power j plus k, where j and k are integers running from 0 to n minus 1. This gives a matrix with the characteristic Hankel style because it's j plus k, and then we form the determinant of these moments where j and k run from 0 up to n minus 1, and this is conventionally written as d subscript n of s. Now this turns out to satisfy a sequence of solutions of Painleve III prime differential equation, and it turns out to be one of the isomonodromic tau functions. This is why this object was interesting. So to be more precise, the particular version of Painleve III we're talking about is going to involve this n, which is the size of the matrix. And the standard way of writing Painleve III is in terms of a dependent variable y and an independent variable x. You have to do a certain amount of change of variables to get this x into the s that we're using. But when you do that, you can introduce what's sometimes called the sigma form of Painleve III primed. And that is satisfied basically by the logarithmic derivative of the Hankel determinant dn of s. So I've written down this formula explicitly, and this is a version of the sigma form of Painleve III primed. There is another way of obtaining the Painleve III primed from the Laguerre unitary ensemble. Forrester and Witte obtained solutions of Painleve III primed from determinants that were Toeplitz determinants rather than Hankel, and they involved modified Bessel functions of the first kind. These are the so-called I-Bessel functions. So that suggested to me that it should be possible to sort of bridge the gap and get solutions of Painleve III primed in the same kind of way as Forrester and Witte, using some kind of random matrix construction. And that's what we're going to do. But it's going to be involving Hankel rather than Toeplitz determinants. We make a further specialization and take alpha equals 0, in which case the scattering function becomes a modified Bessel function of the second kind. This is a so-called k-Bessel function, which you can write with a running variable u and hyperbolic cosine function as an integral of the exponential of e to the minus t cosh of u, and so on. So that's a standard function that arises from the scattering function that I was discussing above. Now, you can build from that a kind of Hankel matrix from the derivatives of your modified Bessel function with respect to t. So I'm going to take this j plus k, which is going to give me the Hankel style of matrix, and then we can form a determinant. I've got to put in some plus or minus signs, but then we can express this as a multiple integral. The formula is a little bit complicated, so I just want to focus attention on particular bits of it. We started off with an exponential of minus t cosh, and you get an exponential of minus t cosh, except it's spread over different variables. The other factor is a product for j less than k of cosh uj minus cosh uk, and this factor is squared. This is a van der Monde expression, and the fact that it appears with a square means that we've got what's called a unitary ensemble. So this is associated with Hermitian matrices. But anyway, this is a standard way of representing such a determinant as an integral over spaces of matrices. The next move is to get rid of the hyperbolic cosine functions, which we do by introducing xj, which is 2 over 1 plus cosh of uj. And then we end up with an expression that's closer to what we had before. And here there's an obvious van der Monde, xj minus xk, again squared. There's a factor in the middle that turns out not to have very much bearing on the outcome. And then at the front, we've got this expression, the exponential of minus t, and it's 2 over xj. And that's similar to what we had in the modified Laguerre weight.
So I'm sorry to interrupt, but we're almost out of time. So if we could, thank you so much.
Okay.
Sure. Because
so
we have
I'll
a
just
session starting soon, right? So yes.
Can I just state one result and then finish?
Oh, absolutely, yes, yes.
Okay.
No, I just wanted to make sure that you knew that.
Okay.
Okay, cheers.
Right. So I'm just going to proceed to just state the result about this. Once you've got yourself into this situation with a certain kind of scalar potential, there's a standard way of introducing what's called an equilibrium distribution, and it's basically the equilibrium distribution of electrostatics. And what you do is you minimize the energy associated with an electric field, which is given by the potential, and a logarithmic interaction term given by points on the line. So we're going to make things a little bit simpler by scaling away some of the terms, and we're going to work with a potential which is 2 over x minus 1 multiplied by 2 psi, and then we've got the logarithmic interaction term, which is 2 log x. And for that, we get this sort of final result. Now, we can calculate the equilibrium distribution quite explicitly. The formula is elementary, and it's not surprising that it is of the following form. It is basically like a semicircle law. The semicircle sits on an interval from A to B, and the semicircle distribution is modified slightly by multiplying by a rational function. We can work out the values of this endpoints of the semicircle, and they're given by a formula such as this one. So this is something one can compute explicitly. And the other piece of information we obtain is that the electrostatic energy satisfies a logarithmic Sobolev inequality in the sense of Voiculescu. Now, what I'm basically saying is that the electrostatic energy for a more or less arbitrary distribution can be compared with the electrostatic energy from a minimizer by means of a certain quadratic integral. Now, integrals of this form were introduced by Voiculescu, and the version that I'm describing here was obtained by Bian. And it's important in this result that we've got a potential that's actually convex. So this is why we've introduced this U naught. But given that circumstance, we have an effective way of measuring how close the electrostatic energy is for an arbitrary distribution P in comparison to the minimizer sigma naught. And it's a free logarithmic Sobolev inequality, so it involves a Hilbert transform of the density P. So this is some extra information one obtains about the solutions, but by considering the approach via random matrices. So I think I'll just leave things there. Thank you for your attention.
Well, thank you so very much. It's time to thank our speakers. I think we have time for about 2 questions, so ask fast. Okay, so there's Peter Schlosser. Oh, that was a clapping. It was not a question. Okay, so okay, so let's see questions in the room. Okay, online. So if you have a question online, please just unmute your mic and ask the question. Right. So there are, no questions from the room as well, which makes us on time. So that is wonderful. Thank you so much for a great talk. Let's thank our speaker again.